Clearing the construction site and preparing the foundation is imperative. This involves excavation, leveling the ground, and ensuring a stable base for the tank's installation. The foundation needs to be robust to support the weight and withstand external forces. Choosing the right materials is critical for the tank's longevity. Materials like steel are often preferred for their strength and resistance to corrosion. The steel plates are fabricated and prepared for assembly according to the design specifications. The construction phase involves the assembly of the tank's components. The steel plates are welded together to form the tank shell. This shell is then reinforced with internal supports and structures to maintain its shape and integrity. The process commences with design and engineering. The floating dome, often made of lightweight yet durable materials, such as aluminum or steel, is carefully planned to ensure it effectively rests on the stored liquid's surface. Engineers calculate the dome's dimensions, considering factors like the liquid's specific gravity and volume fluctuations due to temperature changes or product withdrawal. The fabrication phase involves precision manufacturing of the dome's segments or panels. These segments are crafted to exact specifications, ensuring a seamless fit during assembly. Each section undergoes quality checks to guarantee structural integrity and airtightness. Assembly begins with the careful arrangement of these segments. The panels are connected using specialized welding or bolting techniques, creating a unified dome structure. Gaskets or sealing materials are applied at joints to prevent vapor leaks or emissions. This construction process demands precision and expertise to achieve a perfectly sealed dome that effectively floats on the liquid surface within the tank. Once the dome structure is assembled, it is transported to the tank site for installation. Cranes or specialized lifting equipment are employed to carefully place the floating dome onto the tank's rim. It is then securely attached and integrated into the tank's system. The floating dome's primary function is to minimize vapor space inside the tank, reducing the risk of flammable vapors or emissions. As the stored substance level changes, the dome moves accordingly, maintaining a near constant pressure within the tank. This movement minimizes the substance's exposure to air, thereby preventing oxidation or evaporation. Moreover, the sealed nature of the floating dome significantly reduces the risk of environmental contamination by preventing the release of volatile organic compounds, VOCs, into the atmosphere. The installation involved a 900-ton steel dome, positioned atop the first liquefied natural gas storage tank, showcasing a feat of engineering brilliance. Mechanical fans were strategically placed beneath the dome, employing a meticulously designed approach. Gradually, these fans elevated the colossal 79-meter diameter roof within the 38-meter-high tank. The astounding part: the elevation was executed inch by inch, utilizing a controlled increase in air pressure akin to inflating a party balloon, showcasing the precision and finesse involved in the operation. The entire process of raising the dome roof took the coordinated efforts of the skilled team a mere 3 hours, showcasing their expertise and efficiency in executing complex engineering tasks. As the roof ascended, Welders meticulously secured it to a pre-embedded steel ring within the concrete walls. This final step ensured the stability and structural integrity of the tank, securing the roof firmly in place. This process entails preparing the channel bed to ensure a smooth and even surface, critical for the subsequent installation phases. Channel profiling sets the stage for optimal adherence and uniform application of the lining material. Recently, in La Serena, Chile, Agrotech installed this cutting-edge technology to safeguard a sizable 6.5-meter-wide irrigation channel, showcasing its effectiveness in challenging terrains and demanding environments. The concrete canvas, CC channel lining's pivotal component, the concrete blanket, epitomizes its innovative approach. This specialized material combines a flexible cement-impregnated fabric designed to swiftly transform into a robust concrete layer upon hydration. Its adaptability enables easy transport and manipulation during installation. Once positioned over the prepared channel bed, the fabric absorbs moisture, activating the hydration process within the cement. Gradually solidifying, the blanket molds to the channel's contours, forming a durable, erosion-resistant concrete layer. A pivotal aspect contributing to the durability of CC channel lining is the screwed overlap technique. This method ensures a secure and seamless connection between adjacent sections of the concrete blankets. The hydration phase within the concrete canvas, CC channel lining, marks a pivotal juncture in its transformation from a pliable fabric to a resilient concrete structure. Upon exposure to water or moisture, a chemical reaction triggers the activation of the cement particles embedded within the fabric. This process, known as hydration, sets off a complex series of molecular interactions within the cement, resulting in the formation of calcium silicate hydrate crystals, which gradually interlock and solidify. As hydration progresses, the once flexible fabric undergoes a remarkable metamorphosis, transitioning into a hardened concrete layer. This phase is crucial for fortifying the material's integrity and enabling it to firmly adhere to the channel bed. Through this bonding process, the concrete blanket forms a robust and cohesive protective barrier, resistant to erosive forces and capable of withstanding environmental pressures. The process typically begins at the demolding station. This is where the cured concrete blocks, forming the breakwater units, are removed from their molds. Careful handling at this stage is crucial to prevent any damage to the newly formed blocks. Control station and block transfer to curing line. Once demolded, the blocks are inspected at a control station for quality checks. Any imperfections or defects are addressed here. After inspection, the blocks are transferred to the curing line. Here, they undergo a curing process, which is essential for the concrete to gain strength and durability. As the cured blocks move to the curing line, the emptied molds are transferred back to the concreting station. At the concreting station, the prepared molds are filled with concrete. During this stage, vibrating equipment is used to eliminate air bubbles and ensure even distribution of the concrete within the molds. Laser detection is employed to maintain precise levels of concrete within each block, ensuring uniformity and structural integrity. Any surplus concrete is recovered to minimize wastage. Once the concrete blocks are fully formed and cured, they are evacuated to a designated storage area. Here, they await transportation to their intended deployment locations. The reinforcement process around manholes begins with hot mix asphalt application, ensuring a sturdy base. The asphalt layer is compacted before Geogridn PM placement, enhancing stability. The Geogridn PM, acting as reinforcement, is meticulously placed over the asphalt. The surface is then meticulously finished, ensuring a seamless integration. Finally, a self-leveling manhole is precisely positioned, completing the reinforcement process. This systematic approach fortifies the surroundings of manholes, mitigating potential damage and prolonging the life of the infrastructure. Once the concrete blocks are fully formed and cured, they are evacuated to a designated storage area. Here, they aggregate, sorting, and transport. The process commences with the handling of aggregates, which are sorted based on their granulometry. These aggregates, varying in size, are systematically transported to the concrete plant where the production journey begins. Transportation to their intended deployment locations. Concrete mixing and quality control. At the concrete plant, aggregates are mixed with precise quantities of cement and water to form the concrete mix. Ensuring impeccable quality and traceability, fresh concrete samples undergo rigorous analysis in the laboratory. This meticulous quality control guarantees the structural integrity of the final product. Molding and casting. The prepared concrete mix is then poured into molds of different shapes and sizes, fashioned specifically for the creation of the X blocks. Each mold receives the carefully concocted mix, which is left to solidify into the desired structure. Drying and demolding. The molds, now filled with the concrete mix, are systematically conveyed to a drying line. This critical phase involves a waiting period until the concrete solidifies adequately for demolding. After a thorough 2-day drying process, both indoors and outdoors, the blocks are primed for the subsequent steps. Quality assurance and temporary storage. As the blocks emerge from the molds, they undergo stringent quality checks. Only those meeting the standards set by DMC, the patent holder for the X blocks, proceed to the next stage. These approved blocks are temporarily stored in an area designated for their final inspection and subsequent usage. Transportation and precise positioning. Transportation methods tailored for the project's requirements come into play. Each block, equipped with a gyroscopic device known as PIB and an acoustic camera, is handled with precision. These tools provide continuous updates on the block's orientation, ensuring impeccable positioning. The blocks are then placed with utmost accuracy, guaranteeing their perfect integration with neighboring blocks, a crucial aspect of the dike's stability. The crane, equipped with the necessary lifting capacity, carefully positions itself to support the breakwater. Using specialized rigging and lifting gear, the breakwater is gradually lowered from its suspended position, guided by the crane operator's expertise. This process demands precise coordination and steady control to ensure the breakwater descends smoothly and accurately into its designated position along the coastline, bolstering the coastal defenses. Geogridn is a cutting-edge solution crafted from glass fibers. Leveraging their inherent fire resistance, its composition ensures a level of durability that surpasses steel by threefold, showcasing remarkable resilience against high temperatures with a melting point exceeding 1,400 degrees Celsius. This impressive thermal stability ensures reliability in diverse environmental conditions. The production process employs a sophisticated knitting method, optimizing dimensional stability while minimizing elongation. Not only does this technique fortify the grid, but it also contributes to its eco-friendly nature, being fashioned from mineral raw materials. A patented polymer coating further enhances its compatibility with bitumen, crucial for seamless integration within asphalt applications. The self-adhesive nature of the grid simplifies on-site installation, facilitating a streamlined process. An edge marking indicator aids in accurate overlapping during installation, ensuring precision in its application. Variety reigns with Geogridn, offering multiple roll dimensions tailored to meet specific customer requirements. These grids come in various types, each designed to cater to unique needs, underscoring adaptability and versatility in its application. Rigorous quality control measures validate its strength, boasting an impressive tensile strength of 115 kilonewtons per meter or 665 pounds in. Ensuring a clean, dry surface before applying the grid guarantees optimal performance. Its manual installation is straightforward, pressing the glass grid onto the surface at speeds reaching up to 6,000 square meters per hour. For an even more efficient installation process, a dedicated tractor unit ensures wrinkle-free application, harnessing the grid's excellent self-adhesive properties, especially on leveling courses. Whether for leveling courses or milled surfaces, AdForce offers solutions that excel in trafficability and bonding. The construction of the Quay Wall at the Tema Port Facility using caissons involves a process carefully designed to create a robust and enduring structure. Initially, a trench is dredged into the seabed, reaching a depth of 19 meters. This trench serves as the designated space to accommodate the 74 caissons that will form the foundation of the Quay Wall. The construction of these caissons takes place on land, where each unit is meticulously crafted using an immense volume of concrete, approximately 1,000 cubic meters per completed caisson. This concrete provides the necessary strength and durability required to withstand the harsh marine environment and support the weight and pressures experienced in the depths of the seabed. Once the caissons are fully constructed, they weigh an impressive 2,600 tons each. Maneuvering these colossal structures poses a logistical challenge, but an innovative approach is employed. The caissons are rolled onto a floating dock using specialized inflatable airbags. This method allows for controlled movement and transfer of these massive units onto the floating dock. With the caissons safely positioned on the floating dock, the next phase involves transporting them to their intended locations near the Quay Wall. To achieve this, the floating dock is carefully submerged, allowing the caissons to float on the water's surface. Tugs, equipped with precision and control, guide these massive units into their designated positions with accuracy. Once in place, a deliberate process commences where the caissons are filled with water. This deliberate flooding causes the caissons to gradually sink into the pre-dredged trench, securing their positions within the seabed. This sinking action ensures stability and forms a solid base for the subsequent construction stages. Following the sinking process, the caissons are filled with sand, adding further reinforcement and stability to the structure. Finally, the deck of the quay is cast on top of the positioned caissons. This deck serves as the functional surface where ships will berth and load or unload cargo, requiring precise engineering and construction to support heavy loads and endure constant use. In essence, the careful orchestration of casting caissons on land, their transportation onto the floating dock, precise placement, sinking, and subsequent reinforcement with sand culminates in the creation of a resilient quay wall. Creating printed concrete surfaces is a process involving several key stages. First, delineating the designated areas for printed concrete application is crucial, either by marking boundaries or establishing transition points where the concrete meets other surfaces like tarmac. A robust foundation is prepared, and a substantial layer of concrete, usually around 20 centimeters thick with metal reinforcement, is laid down manually or through concrete pumping. Once the concrete sets, a matrix, similar to stencil painting, is meticulously applied to define the desired pattern or shape for the imprint. Coloring the surface comes next using pigmented mortar containing cement, inert materials, hardeners, and various coloring agents such as metal oxides. This mixture is spread across the surface and smoothed, allowing the concrete to gradually set and the polymers to react, ensuring a durable and adhesive surface. The critical phase involves delicately removing the molds before the concrete fully cures to reveal the imprinted pattern. Progress depends on weather, concrete setting time, and available working hours, impacting the surface area achievable per day. This process results in visually striking and resilient concrete surfaces suitable for both functional and decorative purposes. The assembly of the mold for producing wave blocks like the 50-ton Tetrapods is a crucial step in ensuring precise and uniform structures. Using robust materials such as steel, engineers construct the mold to exact specifications. Careful alignment and calibration of the mold components guarantee the distinctive shape and dimensions required for each block. The assembled mold serves as the template for pouring the concrete, determining the final shape and integrity of the tetrapods. The production of wave blocks, specifically the 50-ton tetrapods, is a fascinating process deeply rooted in coastal engineering. These massive concrete structures play a pivotal role in shoreline protection and stabilization against the relentless forces of waves and erosion. Initially conceptualized in the 1950s in Japan by the Zenichiro Uno, tetrapods revolutionized coastal defense. Their distinctive four-legged pyramid-like design was specifically engineered to dissipate wave energy efficiently. These blocks are interlocked, forming barriers that break the force of incoming waves, reducing their erosive potential on coastlines worldwide. Once the concrete mixture is prepared, the casting process commences. Specialized molds, typically made from durable materials like steel, are used to shape the tetrapods. The molds are precisely designed to impart the characteristic shape and dimensions, ensuring uniformity across each block. The concrete is poured into these molds, taking care to eliminate air voids and achieve a consistent density throughout the structure. Firstly, proper vibration techniques are essential to eliminate air voids and achieve uniform density. Consistent pouring speed and distribution within the mold prevent segregation and ensure homogeneity. Adequate compaction through vibrating equipment aids in removing trapped air, enhancing strength. Additionally, maintaining appropriate moisture and temperature levels during curing is vital for concrete to attain its full strength potential. Adhering to precise mixing ratios and avoiding delays in pouring and finishing stages further contribute to superior concrete quality and durability in coastal environments. The crane, equipped with lifting hooks or straps, carefully hoists the cured concrete block out of the mold. Operators ensure a balanced lift to prevent any damage to the block or the mold. Once lifted clear, the mold is either disassembled or opened, releasing the completed tetrapod. This method allows for controlled and safe extraction, maintaining the integrity of the concrete structure while efficiently reusing the mold for subsequent productions. Wave breakers, like tetrapods, exert significant influence on coastal dynamics. These structures mitigate the impact of waves by dissipating their energy before reaching shorelines. By disrupting wave patterns, they reduce erosive forces and protect coastlines from erosion. Additionally, wave breakers promote sediment deposition, aiding in beach nourishment and stabilization. Their presence alters the coastal environment, influencing currents and sediment transport. While they shield immediate areas, they may cause changes in adjacent coastlines due to altered wave patterns. These structures can create calmer waters near beaches, enhancing safety for swimmers and recreational activities. However, wave breakers might also lead to localized accretion or erosion, impacting ecosystems and habitats. Altered wave patterns may affect marine life behavior and distribution. The production of concrete aquapods, weighing a substantial 12.5 tons each, is a vital manufacturing process that takes place in the scenic and strategically located region of Montenegro. Specifically centered in the city of Kotor, aquapods are purposefully engineered as artificial, unreinforced concrete elements crafted to withstand the unforgiving impact of waves on breakwaters and other coastal structures. These formidable structures are not merely massive in size, but are intricately designed to endure the relentless battering of waves, ensuring stability and resilience against the volatile marine environment. Their unreinforced concrete makeup speaks volumes about their durability and strength, exemplifying engineering ingenuity in confronting the powerful forces of nature. The significance of aquapods in coastal protection infrastructure cannot be overstated. They emerge as indispensable components in construction projects aimed at safeguarding vulnerable coastal areas. Their placement along breakwaters acts as a formidable barrier, dissipating the force of incoming waves and mitigating erosion. In essence, aquapods function as the frontline defenders, absorbing and deflecting the powerful energy of waves, thereby safeguarding the shoreline and the structures behind them. Moreover, the manufacturing process of these colossal aquapods demands precision, expertise, and state-of-the-art technology. Located in Kotor, Montenegro, this specialized production facility employs advanced techniques and machinery to meticulously craft these mammoth concrete blocks. The process involves a careful blend of materials, intricate casting, and curing methods to ensure each aquapod meets stringent quality standards. Attention to detail is paramount, guaranteeing that these structures possess the necessary strength and durability to endure the harsh marine environment for years to come. Anchor Concrete has recently made a significant contribution to the expansion of the 407 extension in Whitby, Ontario, by delivering an exceptional clamshell box culvert. As a toll road owned by the Ontario government, the 407 ETR extension demanded a robust infrastructure solution. Anchor Concrete responded by crafting a custom clamshell box culvert tailored specifically for this project, serving multiple crucial purposes. Spanning an impressive length of 76.6 meters, this culvert is set to act as an underpass for local wildlife, a bridge for motorists navigating the highway, and a conduit for water conveyance. The application of mastic sealant and liquid grouting on the base ensured a watertight seal, fortifying the structure against potential leaks or erosion. The installation process of this colossal culvert was a testament to precision and efficiency. Divided into 2 sections, each piece, weighing an astounding 35 tons, was expertly lifted and placed within a mere 7 minutes, thanks to the innovative cantilever joint design. In a display of remarkable speed and effectiveness, over 2,640 tons of concrete were placed on site within a span of just 4 days. Anchor Concrete's commitment to timely and cost-effective installations not only facilitated the project's progress, but also upheld the 407 extension schedule and budgetary constraints. The installation process for precast concrete segmental box culverts revolutionizes the traditional monolithic box culvert construction methods, drastically reducing time and labor. In typical monolithic construction, completing projects requires weeks of labor-intensive work. Contractors must use tugging equipment to seal box culvert sections in a trench, handling each segment twice. Once to lower it into the trench using a crane, and again to rig it to a pulling machine for horizontal towing over the compacted subgrade. However, with Jensen's precast box culvert design, installation becomes significantly more efficient. The gravity-set tongue and groove system allow each culvert end to be directly lowered into the receiving joint, eliminating the need for tugging sections together. Consequently, this results in tighter joints, free from subgrade aggregates. The swift installation process, completed within 2 to 3 days, contrasts starkly with the weeks-long endeavor of traditional methods. This efficiency means significant time savings for contractors, recovering the 2-week delay that typically occurs in construction schedules. The Jensen precast box culverts offer versatility with 2 designs: Type 1, featuring a U-shaped bottom section and a flat top, and Type 2, composed of 2 U-shaped sections for higher clearance applications. Ranging from 4 feet wide by 1 foot high to 24 feet wide by 16 feet tall, with a standard length of 16 feet, these culverts produce fewer joints compared to monolithic box culverts. Moreover, these precast sections can be engineered to accommodate large pipe penetrations or manway accesses without the need for on-site cutting or drilling, enhancing installation flexibility. The concrete pour process is a crucial phase in construction, especially for substantial structures like the terminal tunnel mat slab at the new SLC construction site. The event on March 3, 2017, marked a milestone as it initiated the creation of a 4-foot-thick mat slab, a foundational element vital for the structural integrity of the terminal tunnel. The preparation for such a pour involves meticulous planning and coordination. The SLC Department of Airports ensured the availability of B-roll footage, allowing media to capture and showcase this monumental event, illustrating progress within the construction project. Prior to the pour, a team of engineers, architects, and construction workers meticulously designed the slab's specifications, determining its dimensions, reinforcement needs, and the type of concrete required. On the designated day, the site bustled with activity. The preparations began with setting up 2 concrete pump trucks, essential for transporting and distributing the massive volume of concrete needed for the pour. These trucks are equipped with powerful pumps capable of handling the flow and pressure required to deliver the concrete mix to the intended location accurately. The logistics were intricate, with numerous concrete deliveries scheduled to supply the required 1,700 cubic yards of concrete. This amount is substantial, necessitating a steady influx of concrete to the site throughout the pour duration. Coordinating these deliveries involved meticulous planning to ensure a continuous flow of materials, preventing any interruptions during the process. As the pour commenced, precision and teamwork became paramount. Skilled workers directed the concrete pump trucks, guiding the precise placement of the concrete mix onto the prepared surface. The thickness of the mat slab required a methodical approach to ensure even distribution, avoiding inconsistencies or weak points that could compromise its integrity. Throughout the 8-hour duration of the pour, the site buzzed with controlled activity. Workers maintained a steady rhythm, overseeing the pouring process and leveling and smoothing the concrete to achieve the desired finish. The attention to detail during this phase is critical, as any imperfections or unevenness could impact the structural stability and functionality of the mat slab. The significance of this pour extended beyond its sheer volume and duration. It represented a critical phase in the construction timeline, signifying progress towards the completion of the new SLC project. The successful execution of such a massive concrete pour showcased the expertise, planning, and teamwork involved in undertaking large-scale construction endeavors. Firstly, engineers and surveyors would outline the canal's path and dimensions, considering the topography and water flow requirements. Excavation machinery would dig the canal trenches, ensuring the precise depth and width needed for the full section lining. Once the trench was excavated, workers would prepare the base by leveling and compacting the soil to provide a stable foundation for the concrete lining. Wooden or metal molds, known as formwork, would be installed along the canal's edges to define the shape and dimensions of the concrete section. Concrete mixing plants or trucks would deliver the required concrete mix on site. Workers would carefully pour and spread the concrete evenly within the formwork, ensuring uniform thickness and quality. Smoothing and finishing the concrete surface would follow, possibly using hand tools or machinery to achieve the desired texture and surface quality. The freshly poured concrete would need time to cure and strengthen. During this period, it would be essential to maintain moisture and protect the surface from extreme weather conditions. What makes the Python 5000 stand out is its one-person operation from within a comfortable, climate-controlled cab. The operator has full control over the machine's functions, using a joystick to position the multifunction tool over the pothole. It's like playing a video game, but with the real-world impact of fixing roads efficiently. This self-propelled patcher doesn't discriminate when it comes to asphalt mix. Whether it's hot or cold, the Python 5000 handles it with ease thanks to its thermostatically controlled double-walled hopper. It can maintain the perfect temperature for hot asphalt or warm-up cold mix to ensure optimal patch quality. The workflow is seamless. Air blasts clear debris, adhesive spray coats the patch if desired. Asphalt travels on a conveyor belt to the pothole, and the operator controls the material application. Finally, the compaction roller seals the deal, creating durable, long-lasting patches. What's astounding is its efficiency. An experienced operator can complete the entire process in under 2 minutes and then move on to the next pothole. This means miles of road can be repaired in a single day, a feat unimaginable with traditional repair methods. Moreover, the Python 5000's versatility shines through its ability to repair cracks, joins, or multiple small potholes in high-traffic areas, all while the operator remains safe inside the cab. Its hydrostatic drive allows it to move slowly, catering to various repair needs efficiently. The implications are enormous. By using the Python 5000 as a preventive maintenance machine, repairing potholes early on becomes feasible, saving time and money in the long run. This machine not only redefines road repair, but also extends the lifespan of roads, reducing the frequency of full resurfacing. Spanning a period of 9 days, from April 1st to the early hours of April 10th, engineers dedicated themselves to the monumental task. Their round-the-clock commitment ensured the successful installation of the new 5,000-ton bridge, a feat made possible through the collaboration of Network Rail, Story Contracting, North Lanarkshire Council, and Glasgow City Region City Deal. Commencing in May 2022, the construction journey of this colossal concrete structure began adjacent to the WCML. This venture, part of a substantial £16.9 million investment, demanded meticulous planning and precise execution. The challenge crescendoed during the Easter period, offering a narrow window of opportunity to maneuver and position the bridge, a task executed with precision and efficiency. The installation of the new bridge deck on April 4th was a culmination of rigorous groundwork. Engineers excavated a staggering 36,000 tons of material from the railway embankment, creating ample space for the new structure. Once in place, the bridge seamlessly integrated into the embankment, heralding a pivotal phase in the project's completion. The ensuing Easter weekend was a hive of activity, witnessing the reinstatement of overhead line equipment and track. This intricate process culminated in tamping, compacting the new ballast beneath the railway track, an essential step to ensure the infrastructure's stability and longevity. Beyond its immediate impact, the bridge's significance extended far beyond its physical presence. Its construction paved the way for North Lanarkshire Council to embark on the creation of a new dual carriageway. The addition of pedestrian and cycle paths from Airbulls Road, Windmill Hill Street, to Robber Hall Road marked a visionary step towards enhancing connectivity and accessibility in the region. This strategic development, aligned with a broader initiative aimed at unlocking the area's potential for future growth and prosperity. The Ravenscraig West Coast Main Line Bridge serves as more than a mere passage. It symbolizes collaborative prowess, innovative engineering, and a commitment to advancing infrastructural development. Its successful completion within the designated timeframe not only underscores the dedication of the involved parties, but also lays a sturdy foundation for the area's socio-economic advancement. The St. Louis Arzviller inclined plane is a remarkable engineering feat nestled within the picturesque region of Alsace, France, along the Marne-Rhine Canal. This ingenious mechanism was designed to overcome a significant elevation change along the canal route, bridging the disparity in levels between the Vosges and the Lorraine plateaus. Spanning a length of 1.35 kilometers, this inclined plane is a marvel of modern engineering, offering a unique and efficient way to navigate the canal. Constructed as part of a canal expansion project in the 1960s, the St. Louis Arzviller inclined plane revolutionized transportation along the waterway. Traditionally, canal systems relied on a series of locks to raise or lower vessels between different elevations. However, this inclined plane replaced 17 conventional locks, streamlining the process of moving boats between the two plateaus. The mechanism functions akin to a water-based elevator, enabling boats to be transported up or down the slope without the need for multiple lock chambers. Vessels gracefully glide onto a large, water-filled carriage, which is then guided along a track using sophisticated pulley systems and counterweights. The entire process is a marvel of precision engineering and hydraulic systems, showcasing the innovative prowess of its designers. Visitors to the St. Louis Arzviller inclined plane are treated to a captivating spectacle of engineering ingenuity. Observing the boats being effortlessly lifted or lowered along the slope provides a fascinating glimpse into the intersection of nature and human innovation. The surrounding Alsace region, known for its charming villages, vineyards, and historic landmarks, offers a delightful backdrop to this engineering wonder. Travelers often find themselves enchanted not only by the technical brilliance of the inclined plane, but also by the idyllic beauty of the canal's surroundings. This feat of engineering stands as a testament to human creativity and the ability to conquer geographical challenges. It remains a point of pride for the region, attracting curious travelers and engineering enthusiasts from around the world. This terminal serves as a critical supply hub, boasting a vast capacity of 20 million gallons for storing various grades of asphalt cement sourced both domestically and internationally via ships, barges, and rails. Moreover, their New York State DOD-approved asphalt emulsion manufacturing facility is equipped with cutting-edge technology, capable of producing and housing a diverse range of emulsion products suited for specific pavement treatments. Their array of surface treatments, road recycling, and pavement preservation processes offer cost-effective options that extend the life of roads by addressing early signs of deterioration, preventing cracks, and applying measures to enhance pavement strength and durability. It involves using high-quality asphalt material to fill cracks in pavement surfaces. By addressing these fissures at their early stages, the process effectively prevents water infiltration, which can lead to more significant issues such as potholes. This technique minimizes the deterioration caused by prolonged exposure to sunlight and extreme temperature shifts. By sealing cracks in curves and areas prone to stress, it helps maintain the integrity of the pavement structure at a minimal cost. Fibermat, a pavement treatment offered by the Geogridn Group, involves using asphalt emulsion combined with strands of fibers. This fiber-reinforced overlay enhances surface strength, preventing further pavement cracking. Micro-surface and slurry seal treatments provided by the Geogridn Group involve applying a mixture of asphalt emulsion, aggregate, and additives. These solutions offer minimal pavement elevation changes, preserving road quality. Paver-placed surface treatment, a technique offered by the Geogridn Group, involves applying an emulsion bond coat directly in front of the paving screed, resulting in an ultra-thin, highly durable road surface. Cold mix paving, a method offered by the Geogridn Group, involves blending aggregates and emulsion on-site. It's utilized for flexible pavement layers, particularly in areas with substandard subbases, ensuring road durability. Recycling, a key service provided by the Geogridn Group, is an environmentally friendly method that rejuvenates roadways. Cold in place, recycling grinds and reuses existing pavement, eliminating potholes and surface irregularities. Full-depth reclamation converts old pavement into a stabilized base course, ideal for severely damaged roads with underlying sub-base issues. Full-depth reclamation, a service offered by the Geogridn Group, involves pulverizing existing roadways up to 18 inches deep, transforming old pavement into a new stabilized base course for enhanced road stability. At its core, this project champions groundbreaking methods tailored to preserve and safeguard the delicate marine ecosystem. Initiated in collaboration with multiple partners, including Tractable, Andromede Oceanology, and ACI, the venture commenced with a comprehensive environmental impact study. This study was pivotal in identifying the ecological stakes inherent in the site and integrating them into the very fabric of the project's design and execution. From the outset, proactive environmental measures were set in motion. Noteworthy actions included the relocation of a substantial number of the great nacre population from the Larvato Marine Reserve, eradicating invasive green algae, commonly known as taxifolia, and transplanting protected species like Posidonia meadows. These initiatives were instrumental in preserving and nurturing the local marine biodiversity. The strategic placement of continuous surveillance devices to monitor water turbidity and the implementation of underwater anti-turbidity screens underscored a commitment to maintaining water quality. Additionally, the construction of a towering acoustic barrier along the coastline from Pont Louis II to Larvato aimed to mitigate noise disturbances for nearby residents. A meticulously planned wastewater discharge chamber, known as the Larvato Chamber, was established, accompanied by the redirection of existing emissaries. These initiatives highlighted a forward-thinking approach to water management and environmental stewardship. The initial phase involved removing the top layer of the Portier Cove seabed, repurposed later to facilitate the development of the new eco-district. Subsequently, dredging operations targeted contaminated sediments, employing specialized equipment like the Mimar Sinan excavator with a sealed eco-bucket to prevent material suspension. These sediments underwent transport to a dedicated treatment facility near Toulon, reinforcing the project's commitment to responsible waste management. Concurrently, measures were taken to minimize turbidity, separating non-polluted sediments using a suction dredger, which carefully transported these materials to a designated environmentally conscious deposition site, preserving marine life at depths of 200 meters. Upon reaching its final elevation, the infill underwent compaction and precise leveling using subsea vibrators, ensuring stability and structural integrity. The completion of this phase heralded the emergence of a sturdy foundation, primed for further development. Simultaneously, in the port of Marseille, the construction of 18 reinforced concrete caissons, crucial for the protective barrier of the new eco-district, was underway, each caisson measuring 26 meters and weighing a staggering 10,000 tons, was meticulously cast within an 11-month time frame using a specially designed structure called the Marco Polo. Once cast, these caissons were floated and subsequently prepared for transport to Monaco. Upon arrival, they were ballasted with seawater, then filled with quarry materials, meticulously ensuring their stability. This meticulous process ensured that sections of the platform were advanced for construction, particularly in areas slated for Renzo Piano's architectural marvel. The culmination of the caisson placement on July 10, 2019, signified the completion of the protective barrier. It paved the way for commencing the construction of the actual platform, utilizing quarry materials ranging in size from 0 to 50 millimeters. The distribution of these materials across the platform was orchestrated using specialized transport boats equipped with conveyors, including vessels like the Stornext and the Nordness.
In the raw material preparation phase, meticulous attention is given to measuring and proportioning the essential ingredients for concrete pipes. Cement, typically Portland cement, is precisely measured to serve as the binder in the mix. Aggregates, which encompass sand and gravel, are carefully proportioned to achieve the desired strength and texture of the concrete. Water, a critical component, is added in precise amounts to create the proper consistency for mixing. Moreover, specialized admixtures may be introduced in controlled quantities to enhance specific properties of the concrete, such as workability, setting time, or resistance to environmental factors. Concrete mixing is a crucial step where the previously prepared raw materials, cement, aggregates, water, and any added admixtures are introduced into a concrete mixer. This mixing process is highly controlled to achieve homogeneity in the mixture, ensuring that all components are uniformly distributed. The mixer's operation is tailored to attain the specific workability and slump required for the concrete pipes. Workability determines how easy it is to handle the concrete, while slump measures its consistency. Mold preparation. Mold preparation is a critical step in the concrete pipe manufacturing process, as it directly impacts the final product's shape and quality. The first aspect of mold preparation involves crafting molds that precisely match the desired dimensions and specifications for the concrete pipes being produced. These molds can be constructed from materials like steel, fiberglass, or other suitable materials, chosen for their ability to withstand the pressure and vibration inherent in the production process. Once the molds are fabricated, an essential step is to coat the inner surfaces with a release agent. This release agent is a lubricant or non-stick substance that prevents the freshly poured concrete from adhering to the mold. Without this coating, removing the solidified concrete from the mold would be extremely difficult and could result in damage to the pipe's surface. Proper application of the release agent ensures that the finished concrete pipes maintain their intended shape and surface quality. Reinforcement placement. In the case of reinforced concrete pipes, an additional step is required before pouring the concrete mix. Steel reinforcement cages are meticulously placed inside the molds. These cages consist of a network of steel bars or wires designed to provide added strength and structural integrity to the pipes. The placement of the reinforcement is a crucial task, as it must be positioned to ensure proper alignment within the mold. Ensuring that the reinforcement is correctly spaced and secured is essential to the overall strength and durability of the finished concrete pipe. Concrete pipe production. With the molds prepared and, in the case of reinforced pipes, reinforced stages properly positioned, the next phase involves concrete pipe production. The carefully measured and mixed concrete is poured into the molds using appropriate methods. Manual pouring may be suitable for smaller pipes, while larger pipes may require the use of an overhead crane or a machine-assisted pouring system. For core vibration concrete pipes, specialized machinery is employed. This machinery incorporates a vibration system that is inserted into the mold. The vibration serves multiple purposes. It aids in proper compaction of the concrete mixture, helping to eliminate air voids and ensuring the uniform distribution of concrete throughout the mold. This compaction process enhances the structural integrity and longevity of the concrete pipes, ensuring they meet the required strength and quality standards. Curing. Curing is a critical post-production phase in concrete pipe manufacturing. It involves maintaining favorable conditions to support proper cement hydration and the subsequent hardening of the concrete. Quality control. Stringent quality control measures are integral to the entire manufacturing process. Throughout each stage, meticulous checks are conducted to ensure that the concrete pipes adhere to required standards. Dimensional accuracy is assessed to confirm that the pipes meet the specified size and shape criteria. Finishing and storage. After curing and quality checks, finishing operations are performed on the concrete pipes. These include trimming excess concrete, smoothing the ends to ensure proper fit during installation, and applying surface coatings or protective treatments as needed.
The 190 miles of PEX tubing create a 4.9-mile loop intricately laid beneath downtown Holland's pavements and sidewalks, ensuring comprehensive snowmelt coverage. The system circulates 5,500 gallons per minute at 95 degrees Fahrenheit. At 20 degrees Fahrenheit, the system can melt approximately 1 inch of snow per hour, aided by 10 miles per hour winds. This efficiency ensures rapid snow removal, maintaining safe conditions for pedestrians and vehicles. It's a testament to the system's effectiveness even in harsh winter conditions, keeping Holland's streets clear and accessible. The Roadrunners Club of America designated Holland as a runner-friendly community, acknowledging its snow and ice-free routes during winter. High-performance tape for pavement marking, excellent long-term results on motorways and other roads. Compost of ceramic spheres, bonded to a layer of highly durable, non-slip and highly abrasion-resistant polyurethane. Reduced replacements, saving Matanacci costs. It features an extended station application due to the pressure-sensitive adhesive on the bottom surface. Thanks to its composition, it offers increased safety and visibility even in the wet. Easy to handle and can be cut to different lengths using a knife or a mechanical cutter. Independent tests indicate that the A380 exceeds all N1436 performance approval requirements. Hog Technologies stands as a paragon of excellence in the realm of pavement maintenance and marking removal. Founded in 1988 by the visionary president and CEO James P. Crocker, the company has remained steadfast in its commitment to quality, innovation, and unparalleled customer support. Over the years, Hog Technologies has garnered acclaim for its groundbreaking solutions, earning recognition as an award-winning manufacturer in the industry. Central to Hog Technologies' success is its relentless pursuit of innovation, epitomized by its flagship product, the Rumble Hog. This cutting-edge machine represents the pinnacle of rumbling, grinding, and grooving technology, setting new standards for efficiency and performance on the job site. Equipped with optional vacuum recovery capabilities, a high-dump debris tank, and continuous offloading functionality, the Rumble Hog stands as a beacon of excellence in the industry. The Rumble Hog's versatility and advanced features make it the preferred choice for contractors and municipalities seeking to enhance safety and prolong the lifespan of roadways. Whether tasked with grinding down pavement imperfections, cutting rumble strips to alert drivers, or grooving surfaces for improved traction, this formidable machine delivers unparalleled results with precision and efficiency. In addition to the Rumble Hog, Hog Technologies offers a comprehensive lineup of cutting-edge solutions designed to meet the diverse needs of pavement maintenance professionals. The Surface Hog provides unmatched surface preparation and cleaning capabilities, while the Paint Hog excels in laying down waterborne paint markings with precision and efficiency. Meanwhile, the Thermo Hog sets the standard for laying thermoplastic markings, ensuring crisp, durable lines that withstand the test of time.
Brighton, a vibrant seaside town on the south coast of England, has always been a hub of innovation and creativity. In recent years, one of the most remarkable developments in the city's skyline has been the Brighton I-360 Tower. This towering structure has become an iconic symbol of Brighton's modernity and ambition. However, what many people might not know is that the construction of this engineering marvel required a critical and intricate undertaking: the Brighton I-360 sewer diversion. The old Victorian brick sewer that runs along Brighton's seafront had been serving the city for generations. However, when plans for the Brighton I-360 Tower were drawn up, it became clear that the existing sewer line would pose a significant challenge. The proposed location for the I-360 Tower overlapped with the path of the sewer, which ran through the center of the tower's massive foundations. This necessitated a delicate and meticulous diversion process to ensure the sewer's functionality while allowing for the tower's construction. The Brighton I-360 sewer diversion project was a complex engineering endeavor that spanned several months, with the work commencing and ultimately concluding in January 2015. At its core, the project involved cutting into the old Victorian sewer and diverting its flow into a new 1,600 millimeters concrete sewer pipe that circumvented the I-360 tower's south-facing foundations. The meticulous planning and execution of this diversion were crucial to maintaining the city's sanitation services while accommodating the new construction. The project began with a thorough survey of the existing sewer line and the proposed path of the I-360 tower's foundations. Engineers needed precise measurements and data to develop a diversion plan that would minimize disruption to the existing sewer system. This initial stage involved surveyors, architects, and engineers collaborating to create a comprehensive plan that ensured both the sewer's functionality and the structural integrity of the tower's foundations. Cutting into the old sewer with the diversion plan in place, the next step was to cut into the old Victorian brick sewer. This was a delicate operation, as any damage to the existing sewer line could lead to sanitation issues along the seafront. Experienced construction crews worked meticulously to ensure the integrity of the sewer while creating the necessary connection points for the new sewer pipe. Cutting into the old sewer installation of the new 1,600 millimeters concrete sewer pipe, the most significant aspect of the Brighton I-360 sewer diversion was the installation of the new 1,600 millimeters concrete sewer pipe. This pipe, which ran around the I-360 tower's south-facing foundations, was designed to accommodate the sewer flow previously serviced by the old Victorian sewer. The installation process required specialized equipment and highly skilled workers to ensure the pipe's proper alignment, sealing, and connection to the existing sewer system. Throughout the diversion project, minimizing disruption to the city's residents and businesses was a top priority. The construction crews worked diligently to maintain access to essential services, rerouting pedestrian and vehicular traffic as needed. They also implemented measures to mitigate noise and environmental impact, ensuring that Brighton continued to function smoothly during this critical phase of construction. Environmental considerations were integral to the Brighton I-360 sewer diversion project. Brighton, with its stunning seafront and vibrant ecosystem, needed protection. Engineers and environmental experts collaborated closely to ensure that the diversion project adhered to all environmental regulations and minimized any potential impact on the surrounding area. The culmination of months of meticulous planning and hard work came in January 2015 when the Brighton I-360 sewer diversion project was successfully completed. The old Victorian sewer had been seamlessly integrated into the new 1,600 millimeters concrete sewer pipe, allowing for the unimpeded construction of the I-360 tower's foundations. With the diversion complete, the restoration phase began, ensuring that the seafront area around the sewer diversion was returned to its former state or even improved.
Measurement and pipe preparation. Before installing a pipe with HK3 as PW connector, it's crucial to measure the required distance for cutting the piping. Consider the intended run length while accounting for the portions of the pipe that will be inside the concrete base once inserted. After measuring, cut the pipe to the required length and ensure that the ends are chamfered and deburred for smooth insertion. Connector preparation. Examine the connector to ensure that the entire circumference has been equally addressed. Lubrication. Thoroughly lubricate the end of the pipe and the interior of the connector. This lubrication is essential for ensuring a proper fit and watertight seal. Be cautious about the type of lubricant used. Avoid hydrocarbon-based lubricants as they can damage the connector material. Pipe connection. If the pipe needs to be connected to another pipe, align the two sections and slowly insert the spigot end of the pipe into the bell end of the downstream pipe section. Ensure it is securely in place. Concrete base installation. When placing a precast concept concrete base into a trench, use appropriate lifting clutches to raise it. Ensure the base is free of any debris on the bottom for level placement. Lubricate both the downstream pipe's end and the outlet of the base that connects to the downstream pipe. Align and connect. Lower the manhole base until it aligns with the downstream pipeline at the same height. Push the base and pipe together to ensure a snug fit. Often a pry bar may be used to assist in this step. Confirm alignment and push the base home until the pipe firmly fits against the rear of the outlet. Leveling and adjustments. Verify that the manhole base and downstream pipe are level. Make any necessary adjustments to ensure proper alignment. Upstream pipe installation. If an upstream pipe is required, follow a similar process as with the downstream pipe. Measure, cut, chamfer, and lubricate the upstream pipe. Align it with the inflow opening of the manhole base and push it home until it securely fits against the rear of the outlet. Final checks. Clear the selected inflow opening of the manhole base from any debris and lubricate it. Double-check the alignment and water tightness of the connections.
Before commencing the installation of pipe culverts, a thorough inspection of the delivered pipes is necessary. This inspection aims to identify any defects or imperfections that may compromise the pipe's integrity. Inspectors should look for cracks, dents, spalls, and any issues with coatings. Additionally, it is essential to review the lifting equipment provided by the contractor and ensure that it complies with manufacturer-rated capacities for the different pipe sizes. Daily visual reviews of the lifting equipment should be conducted to identify and replace any damaged or worn components before use. Maintaining the integrity of the lifting equipment is critical for safe and efficient installation. Excavation for pipe installation requires careful planning and execution. The width of the trench should match the outside diameter of the pipe barrel plus an additional 4 feet. For trenches deeper than 3.5 feet, proper slope-back excavation is necessary, following guidelines provided in RC 30M. Before placing the bedding material, it is essential to compact and proof roll the bottom of the trench using approved equipment, such as self-propelled trench trench-type rollers, single-drum vibratory rollers, or hand-operated compactors. Any areas showing signs of permanent deformation greater than half an inch must be remediated by excavation, drying, compaction, or replacement with suitable material. Proper bedding material is vital for pipe installation. For concrete pipes, bedding consists of ash stone No. 8 aggregate, while metal and thermoplastic pipes require PennDOT No. 2A aggregate material. The bedding should be 6 inches deep, and it should not be compacted at this stage. During pipe placement, ensure that bells or grooves are oriented correctly, with spigot ends fully inserted into the hubs. Lift holes, if required, should be filled with suitable lift hole plugs that are soil tight. Pipe alignment and grade control to maintain precise alignment and grade for the pipe. Use sustainable string lines, electric laser beam systems, or other approved methods. It is essential to maintain a minimum pipe slope of 0.35% for all drainage pipes installed in straight lines. Pipe sections should be joined according to the specified joint requirements in Section 601.3N. Verify joint gaps during installation, and if they cannot be maintained within the specified tolerances, stop work and investigate the cause. Properly sealing pipe joints is crucial to prevent infiltration of materials, which can lead to long-term performance issues and increased maintenance costs. For concrete pipe installations, apply a sufficient layer of pipe joint caulking on the inside of the bell end around the circumference of the pipe. Excess caulk on the inside should be removed after assembly, and the outside circumference of the joint should be sealed with the same caulking material. For elliptical concrete pipes, in addition to caulking, wrap the joint with 2 layers of geotextile Class 1. Metal pipes should be joined using bands with a minimum width of 12 inches, and if the band dimples do not index into each corrugation valley at the pipe end, wrap the joint with 2 layers of geotextile Class 1. Thermoplastic pipes should use preformed pipe joint gaskets according to the manufacturer's recommendations. Proper backfilling and compaction are critical to ensuring the stability and longevity of the pipe system. Compaction equipment, such as vibratory plate compactors or jumping jacks, should be used to compact the sides of the trench. The lateral support provided by tightly compacted material is essential, especially when using shoring or a trench box. The depth of uncompacted material over the crown of the pipe should adhere to specific requirements. For metal and thermoplastic pipes, it should be 1 foot, while for concrete pipes, it should be 2 feet. Follow the guidelines provided in Section 108.05C for specific details on approved compaction equipment and lift height requirements.
Automated cone-laying machines represent a significant leap in efficiency and safety within construction and roadwork industries. These innovative devices are designed to streamline the process of laying cones for traffic management purposes, reducing human labor, enhancing precision, and mitigating potential risks associated with manual cone placement. The core functionality of an automated cone-laying machine revolves around its ability to autonomously deploy traffic cones along designated routes. Equipped with advanced sensors and navigation systems, these machines can accurately detect and analyze the surrounding environment, identifying optimal locations for cone placement while adhering to predefined safety protocols and regulations. One of the primary advantages of automated cone-laying machines is their ability to work tirelessly and consistently without succumbing to fatigue or human error. This ensures that cones are positioned with utmost precision and uniformity, thereby minimizing confusion and enhancing traffic flow efficiency. Snow removal for truck and trailer roofs is a critical aspect of fleet management during winter months. The accumulation of snow on vehicle roofs not only poses a safety hazard, but also increases liability risks for fleet operators. In response to this challenge, Scraper Systems has introduced patented fleet plows, a revolutionary solution designed to streamline snow removal processes and minimize operational disruptions. Fleet plows offer a highly efficient method for clearing snow from truck and trailer roofs, significantly reducing both liability and operational costs for fleet owners. The patented design of fleet plows ensures quick and effective snow removal, allowing for the clearing of one vehicle in just 30 seconds. This remarkable efficiency translates to clearing up to 60 vehicles per hour, enabling fleets to swiftly resume their operations even in the aftermath of severe snowstorms. The key advantage of fleet plows lies in their ability to mitigate liability risks associated with snow accumulation on vehicle roofs. By swiftly removing snow, fleet plows help prevent potential accidents caused by snow dislodging from moving vehicles, such as creating hazardous conditions for other motorists or pedestrians. This proactive approach to snow removal not only enhances road safety, but also minimizes the likelihood of fines or legal repercussions resulting from snow-related incidents. Moreover, fleet plows offer significant operational benefits for fleet managers. By expediting the snow removal process, they enable fleets to maintain their schedules and meet delivery deadlines even in adverse weather conditions.